Hello, this is Mark Anderson from Patties Incorporated in Minneapolis. Today I'm going to talk to you about how to unveil breakthrough synergisms between mixture and process variables. A very powerful way to combine variation of the different components in your recipe at the same time varying the process factors and coming up with the best combination overall that meets your specifications for the product and gives you an efficient process. Our time is fairly limited today, so I need to keep moving ahead on the different topics that I want to cover. Feel free to get back to me at mark@statades.com though with any questions. We'll begin with the layout of combined mixture process designs, and I'll do this by example by looking at a famous experiment on fish patties that a guru of mixture design, John Cornell, developed. Then we'll talk about a more streamlined option that Cornell and others came up with to what is currently done, which are cross models, kind of a brute force approach that gives you a wasteful number of terms. So I have a very elegant alternative for you called KCV. Then we'll look very quickly at the use of KCV to combine mixture not only with process factors but also with categorical variables, substituting materials. And then finally, a very brief look at split plot designs to handle hard to change factors. And at the end, I'll give you some references. So let's come right into John Cornell's famous fish patty experiments. John was a professor at University of Florida in Gainesville, and he wrote the Bible for mixture design for optimal formulation. It's called Experiments with Mixtures. It's in, this references 3rd edition, and chapter 7 covers this experiment of combined mixture and process. So he was tasked with coming up with a better mixture of these elegant fishes from Florida, the mullet, sheep's head, and croaker. I believe they're actually pretty tasty, each individually. However, they have very off-putting names. And the idea was to produce the fish patty for a Whaler sandwich for Burger King that would have a better texture. That was their focus. Hopefully it also tasted good. But it turned out that the texture was fixed in large part not just by the composition of the mixture but also by how it was processed for oven temperature from 375 to 425, time in the oven from 25 to 40, and time of the deep frying from 25 to 40 seconds. So let's take a look at the elements of this experiment. On the left-hand side, we have the element of mixture design represented by this ternary diagram. Some people have referred to this as a phase diagram. And this diagram is very good for any composition. For example, consider a stainless steel, which I would have as part of my material science co-major along with chemical engineering at University of Minnesota. This is when I was introduced to the whole idea. So we start off with A, let's say the nickel, and it's going to go from 0 at the bottom to 100% at the top. And you can see the rulings here, 10, 20, 30, going from bottom to top. Let's say at the left side we've got the iron, and that's going from the right side at 0 to 100% at the lower left. Let's say that C is chromium, and that's going from 0 at the left to 100% at the right. Now, one nice composition for these three metallic elements is 18-8 stainless steel. That makes a nice, stainless flatware. So what is 18-8? 18 to begin with represents 18% of nickel. And you're going to cut a line across like this, and it's reading off 18% from 0, 10, let's say 18. Then we're going to write that down, 18. Then for our second ingredient, that's considered the chromium. And let's go with 8% of that, and that's going to be a line that goes like this, parallel to the left side. Now, once you get the two ingredients, the third is going to be fixed. And we can simply read this off, 10, 30, 50, 74%. And look at this, it adds up to 100%. So once you know any but the last ingredient, that last ingredient is fixed by the total constraint. And this is how we handle mixtures, particularly when we know that the response is a function of the proportions and not the amounts. So that's the idea of mixture design. Now on the right side, we've got a representation of the process factors. And this is a design that is a two-level design where each factor is going low and high. There are 3 factors or 8 runs. And the coordinate system is set up on this so that in standard order, at the lower left front is number 1, which is the low levels minus, minus, and minus of A, B, and C. Number 8 is all the high levels, which is represented as plus, plus, and plus. And in between, we have all the other combinations. Of course, this would be run in a randomized plan. We always want to randomize the order, not do it in the standard order. So now let's put this all together in one diagram, which has the cube with the triangles at the corners. And the cube, of course, is the process with the 2 to the 3 cube. Then at each corner, we've got triangles representing our mixture side of the experiment. And the way this is set up is we've got at the corners the pure amounts of each of 3 ingredients. At the edges, we've got binary blends. And in the middle, we have the overall centroid. And this is called a simplex centroid mixture design. Now, if all 7 blends laid out in the mixture design, the triangles, are done at all 8 process conditions, the cube, then all the terms can be fitted to a crossed 3-factor interaction factorial model with a special cubic mixture model all the way up to a 6-order term, which has got the 3 mixture components, x1, x2, x3, multiplied out times the 3 process factors, z1, z2, z3. And these are the actual models here. This first model is a mixture model. It was invented by a guy by the name of Chaffee. And what we see here are the main component effects in the first 3 terms. We see the nonlinear blending for 2 components at a time, whether they're antagonistic or synergistic. And then finally, we have a 3rd-order term, which is called the special cubic. And actually, oftentimes, because of the chemistry that occurs in a mixture, the special cubic is a helpful term to fit the shape of the surface. Now down below here, we have the process model, which is a factorial model. In this model, we have the overall interceptor average. We've got the main effects of Z1, Z2, and Z3. We've got 3 2-factor interactions, Z1, Z2. Z1, Z3 is a 2-factor interaction. And then Z2, Z3 is the 3rd 2-factor interaction. And then finally, we have a 3-factor interaction, which is probably overkill because generally speaking, in process studies, you don't find it necessary to have 3rd-order terms like this, at least not for the screening and characterization type of studies that we normally apply 2-level design to. But then multiplying out these 2 models, we get 7 terms in the first model and 8 in the second, and a total of 56 terms. Wow, that is really a brute force approach. Well, I guess Cornell and his graduate students had lots of time to spend at University of Florida back when they did this study, because they did all the possible combinations of 3 process factors. And you can see the standard layout going minus, plus, 2 minuses, 2 pluses, 4 minuses, 4 pluses, and then of course we would do this in a randomized plan on the left-hand side. Then for each setup of process factors, they ran a series of different mixture compositions going from all of the first fish, all of the second fish, all of the third fish, binary blends of fish 1, 2, binary blend fish 1 and 3, binary blend fish 2 and 3, and then a 1/3, 1/3, 1/3, which is the overall centroid. Now what is fun about this is we've got all the data tabulated, and considering they're trying to get somewhere between 2 and 3.5 for the texture, we end up seeing some very promising results where some are below the range and some are above, but we get a fair number of them in that 2 to 3.5 range, which I'm just kind of circling here because this is an ideal scenario of having some in the range, some above the range, and some below the range. And when that happens, you're more than likely going to get, a good model out of it. It's going to be significant and useful. And so I don't know if I'm circling these quite right, but you can see different zones here. And for example, here's one at 2.75, which is right at the midpoint of our range. And that's done with all the plus levels of the process factors. And it happens to be all of the third fish, for example. Now, whether this is the ideal combination depends a lot on economics, right? How much did these fish cost? How are they available? And things like that. So what's cool about this modeling is we can use this predictive model, the KCV model now, that's been, fitted and we've got good statistics for and hopefully confirmed. And now we can use this as a what if under the covers of the software to try to unveil desirable results given the circumstances. So for example, what if croaker was readily available? There was a glut on the market. However, everybody's trying to buy it because it's so cheap, and the most we can get for our fish patties is enough to make 15% of the patty. Then what you can do is you can set the croaker equal to 15%, which is what we've done here. Now let's assume that sheepshead is cheaper than mullet. So what we're going to do is maximize the sheepshead. We've created a desirability ramp here from 0 at 0 to 1 at 100. So we're trying to drive the sheepshead up as far as it can go. Then on the other hand, the mullet, which is a more expensive fish, we're just leaving that within the constraints. And it turns out we need to have some mullet to be able to get the texture to where we want. However, we're not done yet. We also can fiddle with the process factors, the oven temperature, which is going to stay within the range of 375, 425 for our search, oven time between 25 and 40. And then it turns out deep fry didn't have much of an impact on any of the results. So we just conveniently set that equal to 30 seconds. So with these parameters set up, then the search is done, and we're able to get the texture right on target. If we put in 61.3773 or approximately 61% of mullet, we're going to have to do that. With that, we can then get as much sheepshead as possible while maintaining the croaker at 15%. So this is a very successful approach to contend with both the mixture and process variables. And then I've got a couple of model graphs to show you. This one is in the square or orthogonal space that you normally would work on with process factors. And what we've done here is actually pretty cool. We've got one dimension being a process factor oven temperature, and then by ratioing 2 of the 3 ingredients, we can create another axis here, in this case a mullet to sheepshead ratio. And this flag is representing a combination here of what the oven temperature is and what that ratio is, a mullet to sheepshead, that gives you the 2.75. Now with the software, you have a control panel, and you can fiddle with these slide bars and move the croaker amount up and down to see what happens. You can change the oven time up and down to see what happens, and that'll cause the surface to go up and down. And then the deep fry, which you'll see doesn't have much of an effect if you try this, because when you slide this bar, it hardly changes anything, if anything at all. Now a flip view of this is looking at it from the mixture point of view. In this case, which I actually prefer, we've got all 3 ingredients, the 3 different fish at the corners here. The binary blends are going to be along the edges of the triangle. And in the middle are what are called complete blends that have some of each of the 3 fish. And that's what we need here to get to the 2.75. And we pinpointed that, I showed you that earlier with the red dots on the multiple response optimization. Now again, we can fiddle with this, but it's a little bit cleaner, I think, to keep the mixture in front of you like this and then change these process factors by changing the slide bars and see how this surface goes up and down and how it changes. So with the software, you can create a very dynamic presentation to really understand how these fish patties work. Well, let's look at a streamline option, and this is called the KCV model after Cornell and his collaborators, Scott Kowalski, who did most of the work as a graduate student, and his advisor was Jeff Vining from Virginia Tech. The 3 of them collaborated, and they recognized that standard cross models have way too many terms. We don't need all those to detect likely interactions between mixture and process. So they considered a very elegant solution. What if we only cross the linear terms? Then we simply add the mixture and the process terms beyond that. Then applying this model for an optimal custom design will save many runs, yet it still will detect the most probable combination effects. Also, you can include categorical variables in this KCV, so you can have mixture, process, and categorical. So how does this shape up? Well, the cross model would have 56 coefficients. We talked about that, including, big terms like AD squared, ABCD, ABCD squared, etc. It would be very wasteful. But this KCV model only needs 21 coefficients, which are the main component effects, which are locked down because you've got to have something into the fish patty. It can't be nothing. Then we skip ahead to interactions that show you the nonlinear blending effects of A and B and A and C, and here's a BC. But these are the terms here that give us the crossing. For example, in this first set, we're crossing the component A with the three factor terms D, E, and F. Here we have component B crossed with D, E, and F, and C is crossed with D, E, and F in this next group. Then we shift to purely process factors at the bottom, and here we have the interaction of D and E, D and F, E and F. Then these squared terms are called quadratic terms, and they'll give you the nonlinear factor behavior from that. So it's a very interesting model. It's kind of a hybrid. But generally, it cuts the design size down by 50%. Wow, that's huge. But it still works. So let's look at an example. This one is an example of combining mixture and categorical experiments on a composite material. And these aerospace engineers were trying to maximize impact and tensile strength of this epoxy fiber composite by varying the materials as follows. It's a 4-component mixture, A, B, C, and D. Components are elastomer, 5 to 20, fiber, 56 to 62. Hardener is left unconstrained from 0 to 100, and epoxy is unconstrained from 0 to 100. But it turns out that there is a constraint, which is actually a ratio constraint on the epoxy to hardener, has to be kept between 1.8 to 2.1 on the stoichiometry. This is entered in very easily with the software that's dedicated to this purpose. With what's called a multilinear or multi-component ratio constraint, you can literally enter in that C to D has to be between 1.8 and 2.1, and after that it'll never go outside of those ranges. Now what's interesting is they also substituted in for the elastomer 2 types. We call that factor E. And then for the fiber, 3 types. We call that factor F. These are categoric factors. So we've thrown together a lot of things into one experiment. If we were to develop the models and just simply cross them in a brute force way, it would require 60 unique combinations for the 60 terms in the model. And even there, we're doing it only for the 2-factor interaction process model and only for the quadratic mixture. We're not doing the special cubic this time. But even so, it still takes 60. That's too many. With the KCV, which crosses only the main or linear effects terms, we end up with only 24, which is, much better. And the source of this experiment, we talk about this in our mixture design for optimal formulation workshop that Patties presents on a regular basis. So then the data are fit to the KCV model. It's reduced to eliminate terms that are too high in p-values, and we end up with a reduced KCV model. And when we apply that model, we can then find the most desirable settings to give us the maximum impact and maximum tensile. However, to be more exact, we want to set our goals with a lower threshold limit and an upper threshold limit so we can kind of trade off these two responses. So for the impact, 100 was considered to be the lowest that they would accept. Below that would be 0, desirable. And then 140 was considered, good enough. So anything above 140 is desirable, desirability of 1. Then for the tensile, they set 1200 at the lower end. Below that it's 0, and 1400 is as good as they need to get. So this gives us a way to trade things off, and we start from all the design points and do a hill climbing search by plugging in each set of coordinates to our predictive equation, predicting both the tensile and the impact, measuring those against the desirability ramps, multiplying the desirabilities together, and then coming up with a combination that gives us the maximum overall desirability. And it eventually converges on elastomer at approximately 9%, fiber at 62%, hardener at 9.3%, and then the epoxy resin at 19.5%. And so we're able to maintain the ratio, of course, that we were looking for of epoxy resin to hardener. That's been built into the program. And then it's doing this with the second elastomer type and the second fiber type out of 3. Now this is just a first cut. You then would want to go back and consider, what are the expensive ingredients? If certain ingredients are quite expensive, then you're going to set up goals on those individual ingredients. Like if elastomer was very expensive, we want to set a driving force to try to get that closer to 0. If fiber is really cheap, then we could say let's maximize that. And you can even put a cost equation in that would include all this information, and you can minimize the cost as well as trying to meet your targets for the maximum. There's a lot that can be done with the what if.